So just tell me, those who are in online, can you see my slide? Can you see my slide? Is it okay? Fine? Okay. You can put it on the chat. Good. Fine. This is okay. This we did in the last class. Right? When we modulate a signal, it has more than one frequency. Right? In such cases, okay, when you find the power, total power, that in expression, you will have two modulation indexes because the amplitude of the signal is different, right? Frequency is also different. That's why you get two amplitudes. Okay. So hence you get two modulation index. The effective modulation index is equal to square root of sum of the square. Okay, you can see here m of t is equal. See, in earlier case, when we started with amplitude modulation, we started with m of t is equal to just en cos omega n t. That's all. But now the message signal has two frequencies in this particular case. Okay, that's the only difference. Okay, so finally you will get a an expression like this. Okay, you will get a an expression like this. Now, when you calculate the power for this, I told you in my last class how to calculate the power, right? When you calculate the power for this, you get this expression. See, total power is equal to this. In this expression, okay, you take AC square by 2 as a common, okay, AC square by 2, okay. This is into, okay. This is, you are taking AC square by 2 common from here, okay, into 1 plus m1 square plus m2 square by 2. This can be regarded as mt square, where mt is equal to square root of m1 square plus m2 square. These are called as modulation indices, right? Okay, you understood now? Okay, right? These expressions are very important. Now, let us generalize this for a signal with n frequencies. It's not only two frequencies present in a signal, right? This m of t, it may be a1 cos omega 1 t plus a2 cos omega 2t plus a3 cos omega 3t plus a4 cos omega 4t dash. It's possible, right? A signal may have multiple frequencies. Okay, in such cases, what is the effective modulation index? Okay, so we can generalize it as, in general case, we can say effective modulation index. Effective modulation index is mt is equal to m1 square plus m2 square plus, sorry, it is m3 square, okay, plus m4 square and dash. Okay, so whenever you have been given a question where signal has multiple frequencies with multiple amplitudes, okay, then you will have to use that particular modulation index, okay, and then substitute it. Yes, tell me, sir. Previous slide, okay, fine. This is the one which I have stopped. This is the place where I stopped. Okay. Fine. The difference in this equation and the earlier equation, only m of t, that's all. It's totally mathematics, right? Earlier, you know how to find out the power. In this equation also, you know how to find out the power, right? And you get this mt square, that is equal to square root of m1 square plus m2 square. This m1 and m2 is the modulation indices. See, there you have a1 cos omega 1t plus a2 cos omega 2t. What is m1 there? Tell me. M1 is a1 divided by the carrier AC, right? M2 is equal to A2 divided by AC. That's why I told you this is not plus, this is into. That's why I told you it's a mistake. Because AC square by 2, we take it common. Right? Right? That's a mistake there. AC square by 2 is equal to PC. It's the carrier power. Right? Here it is into. There's a print mistake there. Fine. Any doubt in this? Okay. A simple expression, very simple expression. It is not difficult at all. Right? Okay. This is generalization. Earlier we took only M1 and M2. Suppose you have a signal with multiple sine waves added together. Then your just MT is equal to this one. That's your power injection remains fixed. Right? In tutorial class, I will give you some problems on this. Okay? So you can do those problems at that time. Okay? But see that your modulation, effective modulation index should not exceed 1. It should be always between 0 and 1. Okay? Take down this. Take down this. Can you do this? Do this now. Okay? How to do this? Is the question. Obtain the modulation index and efficiency of the signal. That 0.5 and 0.2 is given to you. Right? Okay, so how do you obtain? I will go back to the spectrum. Just see, I have done, see. Now can you do that? Right? This one you know, right? Okay? I'll go back to this. Now can you get me the modulation index? When the x-axis is frequency, I told you what will come in the amplitude, corresponding amplitude. Now can you get me the value of modulation index? You can do it. So those who are in online, you also have to do it. Look at the problem. Just look at the problem. Can you calculate M modulation index now? How do you calculate modulation index now? What is that 0.5 equal to? AC by Q, right? We get AC value. What is that 0.2 equal to? M AC by 4. You got it? Okay. So you do this problem on your notebook. Exactly at 10:30, you will get a link to upload that. Okay. So after this class, you will get a link to your Google Classroom. Whatever you have done, you upload it. Yes, this problem. Fine. Upload the answers. Right? So you need not upload now. Okay? You need not upload now. You'll get the link. Now you have not got the link. You'll get the link to your Google Classroom. Just whatever you have done on the notebook, scan it and send it to them. Upload it. That's all. Not now, not now. Don't worry. Okay. Fine. You understood. Can you tell me what is the answer? What is the answer to modulation index? Say 0.5 equal to, I'm using board. 0.5 is equal to, it is AC by 2, right? In the spectrum. So what is AC? AC is equal to 1 volt. Right. Now what is that 0.2 equal to? This has been done earlier. I have done this in the previous class. Okay. What is 0.2 equal to? Modulation index into AC divided by 4. I have done this in the class. You should remember it. Right. Okay. Now what is M? What is MEAC? AC is 1, right? Equal to 0.8. What is M? M is not 1. How M is 1? 0.8. This is into 1. This is the answer for this problem. See, this type of problem you have to understand. See, if you understand the concept in communication systems, you can do any questions related to this. Try to understand every point in this. Right? Okay, fine. Okay. Now, more problems will be given to you. Don't worry. In tutorial, I will give more problems. As much as possible, it will be done in tutorial. And tutorial also, you will have some question evaluation. Okay. So, you will get one link at the end of the tutorial class. And whatever you have solved, okay, for whatever question asked, you just upload it, do it and upload it. Within that time, we will not be given extra time. Fine. Okay. So be alert and attend all the tutorials and all the classes. This type of evaluations may be there in the class. Right? Okay. Fine. Okay. This one you understood, right? Okay. Yeah. Now, how to generate this? Let us see how to generate an A modulated wave. Okay. How to generate this A modulated wave. All of you know at this point what is an AM wave, right? You all of you know what is an AM wave, okay? And what is its equation? My dear, last person, keep your mobile inside, man. Right? You don't need any mobile right now, right? What is an AM wave? You all know at this point of view. You know its mathematical expression. You know its equation from frequency domain view or frequency domain point of view, by which you also know its spectrum. You know what is the total power transmitted in the antenna. You also now know what is total current, right? What is the total current? IT into square root of 1 plus m square by 2, right? When you know power PT is equal to PC into 1 plus m square by 2, of course, current is equal to IT is equal to IT into square root, because you know power is equal to I square into R. Consider R to be equal to 1 ohm, you get I, total current. Right, okay. Now let us see today how to get this wave electronically. Right, we have to generate this waveform, right? It is not that only in theory these are applied. We need to know how to generate it. Okay, let us see how to generate AM modulation. We call it as modulators, right? Modulation is theory. Modulators are the physical device, right? Okay. So I think those who have done amplitude modulation in the laboratory, right? You have used kit. Yes or no? You have just used kit, right? What is there inside the kit? Have you observed? Anyone has observed? What is there inside the kit? Any circuit? Have you drawn the circuit, transistor circuit? circuit inside that? Yes or no? How many of you have done EM base? Tell me. You have done EM base. You have done EM base. Okay. Right. Have you seen how it is generated? Hmm? Any circuit inside, which you get some knowledge that how AM modulation is done. It's not magic, right? You have got AM modulated waves, right? You have observed that waveform on this year, on the oscilloscope. Now, MATLAB is different. I'm talking about MATLAB is just in MATLAB is just a simulation. MATLAB is a mathematical tool. It's a matrix laboratory. Right? I'm talking about in hardware. When you do amplitude modulation in laboratory, in hardware, right? You have used the kit, right? You have given the input and we took the output. Have you observed how exactly what is there? Which IC is there to do that? Right? You know that. Right? Okay. Let's see here now. Right? What is this? You have a microphone and there is an audio amplifier there. That's an audio amplifier. Okay. All of you have done microelectronics, right? Last year. You know what is an amplifier, right? You know what's the transistor amplifier, right? Okay. So I need not explain you what is an amplifier, right? So because microphone picks up, it's a transducer, its amplitude is very small. So that you need to amplify, use an amplifier, right? So you have done so many amplifiers in microelectronics, you know it, what is an amplifier now, right? Okay. So now after that, it is fed to amplitude modulator. Can you see you can see, then it is fed to amplitude modulator. Can you tell me what is this radio frequency oscillator? What's the purpose of this radio frequency oscillator? Radio frequency oscillator. See, what it gives to the carrier, exactly carrier. Your carrier is in the radio frequency, right? Radio frequency is in the 50 megahertz range. It's all called radio frequency, right? Now, see, amplitude modulation is modulate, and you have a carrier connected to that, which we call the radio frequency oscillator. Can you tell me, see here, you have RF power amplifier. We need a RF radio frequency power amplifier. Why we need to amplify the power? Tell me. Because this signal has to travel for a longer distance, yes or no? Right? The power in the signal may not be enough that it can travel through the longer distance to an antenna. That's why its power is amplified. Right? So that's why an RF power amplifier, it's not a simple power amplifier. These power amplifiers are working in radio frequency range. You all know this dependency of frequency on amplifier. This is in microelectronics. Yes, sir. Tell me, come on. In microelectronics, you have seen amplifier and you are seeing its frequency characteristics. Yes or no? Frequency response. Have you seen frequency response? Right? So what happens in high frequency, what happens in low frequency, all the things we know, right? So we need to design an amplifier, a power amplifier, which works in the radio frequency. The design is different. An amplifier working in the audio frequency is different than an amplifier working in the radio frequency. I understand this. Okay, that's why RF. Okay. Now this is actually a transmitter. If you talk about transmitter, this is a transmitter, but this is an AM transmitter. This is an amplitude modulation transmitter. Right? Okay. So now in this, we are not going to look at audio amplifier and RF amplifier here. It's not scope of this course. Already you have done it in microelectronics. Okay. Now let us see about amplitude modulation. Okay. So there are different types of modulators available, right? There are different types of modulators available in the literature. Okay. So one of the modulators, we call it as a switching modulator. Switching modulator. And this switching modulator works based on the square law, or what is called as a square pulse train. Okay, this works based on the square pulse train. Okay. Now, what is he directing? Simple diode circuit with an oscillator there, right? You can see a simple. What is the circuit called? The Wheatstone bridge, right? So you have come across with the similar circuit in, especially in rectifiers, right? In full rectifiers normally used. Yes or no? Hmm? So now, purpose of this arrangement, okay, is to get a switching action. Okay, get a switching action, right? See, you are actually supplying a carrier waveform. Okay, AC cos omega CT. It's an oscillator. Are you knowing about oscillator? What is an oscillator? What is an oscillator? I'm just bringing this to you because there is a term called oscillator there. So this is, if you have a symbol, something like this, if you have a symbol something like this is an oscillator. What is an oscillator? Can somebody tell me about oscillator? It generates oscillation of any frequency. It can be sine wave, it can be square wave, it can be triangular wave. It generates an oscillator. Okay, right? That's called as oscillator. Okay. Now here, what you can see here, okay, can you tell me what happens during positive half cycle and what happens during negative half cycle there? I just want you to analyze it. There's an oscillator there. Okay. What happens during positive half cycle and what happens during negative half cycle? Hmm. Just you have to tell me the output across A and B. What exactly you are generating there? Tell me. Just small step for it. If you think more, you understand more, right? Right. So what exactly generates? Ah. Hmm. What it generates? Ultimately, what it generates, tell me. It will generate a, is it a wave? I'm just talking about this, what this will generate between A and B, what this will generate. Your oscillator is this one. It generates this. This is what happens. That AC, this is your AC cos omega CP. This is your AC cos omega CP. This is AC. Okay, now this is supplied to this. Ah. During positive half cycle, what will happen? Which are the just see, which are the two diodes conduct? When C is positive and when during positive half cycle, C is positive, D is negative, right? Okay, then what are the two diodes conduct? At a time, two diodes will conduct. See, during positive half cycle, you will have a positive Okay, right? During negative half cycle, you will have a negative switch there. Okay, so this is acting like a switch, right? And switching on and off, okay, is decided by the frequency of the, right. See, during positive half cycle, you get like this. See, you get a square wave. It acts like a switch, right? See, during positive half cycle, okay. See, during positive half cycle, so which are the two diodes followed by here? Tell me, D1 and D2, right? Okay. During negative half cycle, which are the two diodes, right? Okay. Now, is it not acting like a switch now between A and B, right? Right. See here, between A and B, okay. It is now acting like a switch. During positive half cycle, these two will conduct, but this is having negative terminal here, yes or no? Right? Here it is having negative here. Right. Now, during negative half cycle, this will conduct. So this is acting like a switch. Ultimately, see here, ultimately what is generating here between A and B? A square wave, a square wave. A square wave is generated between A and B. Right? Between A and B, what you have is a square wave. See, it is going to be fitted here, see. Right? It is going to be fitted here between A and B. This is called a series bridge. This is called a shunt bridge. So this is acting like a switch based on the frequency of this AC cos omega CC. Now, we will see another circuit similar to this. See this. This is called as ring modulator. This is called as switching modulator because this acts like a switch for this waveform. Acts like a switch means during positive half cycle, this will be on, right? Negative half cycle, this will be off, right? So like that it continues. Right? It all depends on these 2 points. See, during positive half cycle, these two will be on, right? Right. Okay. Now you just try to do the connection from here to here. Is there any connection? Right. Now during negative half cycle, okay, this will be negative, right? Yeah, correct. D1, D2, between when you connect this to A, connect this to B, okay? This is conducting and this is not conducting. Okay. And during negative half cycle, this is conducting and this is not conducting. Okay. 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 So what you're going to get here is a square wave. How to get a square wave? Okay. How to get a square wave? See, this diode is saturates at some point, right? Now, your input is this one. Your input is this one. Okay. From the diode, your output will be a square wave. right? Your input is AC cos omega CT to this, okay? Now, at A and B point, you will get a square wave. And now, you may be having questions. Why you generate square wave between A and B? Right? What we are doing here is, your input is M of T, right? M of T is the message signal, right? What you're doing here is, you are multiplying M of T in this circuit with this square wave. Why we are multiplying this M of T with the square wave? Because this square wave, the square wave can be represented using Fourier series expansion. What is the Fourier series expansion of this square wave? That's why I told you see the Fourier series. What is the Fourier series expansion of the square wave? Right. Fourier series expansion of the square wave will give you, okay, this square wave frequency is omega c, right? This is the waveform between A and B for this carrier signal. Okay, this is what you get. Okay, this is square wave. Okay, now this square wave can be represented using Fourier series representation. The Fourier series representation of the square wave, see, it's something like this: 4 by pi cos omega ct minus 1 by 3 cos 3 omega ct plus 1 by 5 cos 5 omega ct. This is the Fourier transform of this square wave. And this square wave is generated by this ring modulator and also this switching modulator. Now, let us see which is better later. Let us first understand why we are doing this. Right? Why we are doing this. Okay. After that only let us see it is better. Right? Okay. Now, after doing this, where we get, see, what we are generating is double sideband suppressed carrier, not even wave. What we are generating is double sideband suppressed carrier wave. What is double sideband suppressed carrier wave? Suppose this is your M of T and this is your carrier cos omega ct. What is DSBSC? M of T into cos omega ct, right? This is what your DSBSC is. Now, what we're doing here is, M of T is anyway it is there. Then you have this square wave, right? Now you multiply that. What you will get? This square wave can be represented like this. See here, try to understand this. See, the square wave can be represented using Fourier series expansion. All of you know Fourier series expansion. This is very important. That's why I told you signals and systems are very, very important. Now, the Fourier series expansion of the square wave is this. I have given you, today I have sent you some 2 slides, okay, for Fourier series. Okay. This Fourier series you have done not only in signals and systems, also in mathematics, yes or no? Right? Okay. Now, if we take the Fourier series expansion of this square wave, what you will get? You will get this, definitely 100% you get this. I'm not going to do it here because it takes lots of time. Right? And you only done it in your previous class. It's not that it's not done. Okay. Now, you multiply M of T with this Fourier series expansion. What you will get? Tell me. Come on, try to understand this. If you multiply, what exactly you're doing here in this circuit is M of T is multiplied with that switching modulator. The switching modulator generates square wave. And the square wave can be represented using Fourier series expansion as this one. So, M of T is there. M of T multiplied by, okay, square wave. That is what you're generating here. That is what you're generating here. See, m of t multiplied by square wave. Here getting square wave. This is the circuit here. Okay. Don't, this I will tell you why band pass filter. Okay. Now, so this multiplied by this. Okay. This is represented by Fourier series expansion. What is that? Yes. It's just a square wave generator. You can see it generates square wave. Yes. This is a square wave generator. You're going to fix it here. So m of t multiplied by square wave generator. This generates square wave for this. Why constant voltage? If you put constant voltage, it is just a constant. It will become a constant multiplier. You need to have a square wave generator there of any frequency. Square wave will be generated between here. Why you want to put constant voltage here? I don't understand. This generates a square wave here. Okay. Now, m of t is fed into this. M of t and this is multiplied here. Let's understood this. Okay. M of t and this is multiplied here. Now, m of t is multiplied by the square wave. What is how the square wave represented here? See here. This is the square wave. 4 by pi. Okay. Cos omega ct minus 1 by 4 cos 3 omega ct. Now you tell me what term in this will give me ds/dsc plus 1 by 5 cos 5 omega ct. 1 by 5 cos omega ct. When you multiply this square wave, which is represented using Fourier series expansion, and m of t, okay, individually multiply this. Multiply this and this one. Is it a ds/dsc? You multiply m of t and this term. Is it ds/dsc? Come on, why can't you answer me? What is ds/dsc here? M of t into cos omega ct is the ds/dsc. I don't understand why you're so dumb. Okay, you multiply this term, and this term. Out of these three, this will continue. Out of this term, which one is the ds/dsc? Of course, which is that? M of t into cos omega ct. 4 by pi constant anyway, it is there. M of t into cos omega ct. So this term alone is going to be your ds/dsc. So these terms are not required at all. So what was the frequency of this? This is 3 omega c. This is 5 omega c. Right? This is 5 omega c. And you get dash. Definitely, this will multiply m of t here. This is m of t here. Listen here. You are right. But can you see there is a band pass filter there? You have a band pass filter. Okay. Of course, you have m of t multiplied by everything. You get m of t this term, m of t plus m of t this term, m of t this term. Now, after the band pass filter, with the center frequency omega c, right? Do you get all other frequencies? No. That's why after this, you have a band pass filter. And this band pass filter, its center frequency is omega c. Now understood. Now after band pass filter, can you tell me what term will come out of this equation? Only m of t into, I'll put 4 by pi here, into cos omega c, cos omega ct. All these terms will be filtered out. Filtered out. Can you tell me what is this now? What is this now? This is your double sideband suppressed carrier wave. Now, what is important here is understanding the square wave. Like, see how mathematics and your actual square wave is related here. When I put it in terms of mathematics, you understood why the square wave generator is put there. Right? Okay? Huh. See, here you have the. Of course, that's what required now. See, what you are doing, it's adding only. It is adding only. Amplitude of this is varying according to this. That's what modulation is. That is what modulation is. Mathematically, you get this. Band pass filter, you don't know. Come on, listen. Band pass filter, it passes certain range of frequency, okay, and it removes all the frequency component in the signal. That's called band pass filter. Exactly. See, in this, we want only omega c, right? We don't want 3 omega c. We don't want it. Remove all the components and keep only omega c. Now, have you understood requirement of signals and systems here? Signals and systems are very important for your DSP, for EC students, and also here. Right? Have understood this. Now, see here. Principle is very simple. It's a very simple principle. M of t is multiplied by a square wave. Okay. Now see, now I am multiplying your signal, message signal M of t. It can be anything. I am writing a general M of t here. Okay. Fine. Multiplied by the square wave. This, you may be wondering why M of t multiplying with the square wave, you are getting a double sideband suppressed carrier M wave. Here is the proof. Is it not a proof here? A square wave can be represented using Fourier series expansion, right? When you represent a square wave, periodic signal, it's a square wave using Fourier series expansion, you get this. Now, in this, you have M of t into cos omega ct, M of t into cos 3 omega ct, M of t into cos 5 omega ct. Now, here, somewhere one term is corresponding to the one which you require, yes or no? That is your double sideband suppressed carrier wave. Other things you don't require. What you do, you use a filter, you use a band pass filter with the center frequency omega c. What that band pass filter will do? It will keep only that omega c component and remove all other components. So finally, what you will get? Only M of t into cos omega c into c. Have you understood this? Then what is M of t into cos omega ct? It is double sideband suppressed carrier AM wave. You got it? Have you understood now? Is it clear? Okay? Fine. Okay. Now, this is called a switching modulator. This is called as ring modulator. So what is the difference between these two? Only the diode arrangement is different, that's all. Only the diode arrangements are different. Principle is same. Here also you are generating a square wave, multiplying it by M of t. Okay? See the circuit here. You have M of t here, which is connected to a transformer. Okay? And see here, this is your carrier signal, which is connected to these 2 points. So this circuit is going to give you a square wave. Okay? And then M of t multiplied by this square wave, that is W naught of t. Okay? And that is connected to now a band pass filter, what you get Km of into cos omega c. This is called as ring modulator. Okay, so how it works? See, during positive half cycle, okay, during positive half cycle, see this. This is during positive half cycle of this. Okay, so what happens? Your diode B1 and B3 is on, right? During positive half cycle, right? Diode B1 and B3 is on. Okay. Now, what will be the output now? Output is proportional to M of T, yes or no? Right. Okay. Now, during negative half cycle, these two are on. Okay. Now, output is proportional to minus M of T. Right. So, what exactly you are getting? Switching, right? M of T minus M of T. M of T, in earlier case also same thing you are getting, right? M of T minus M of T. M of T minus M of T. Right? M of T minus M of T. M of T minus M of T. Okay. And what is that M of T minus M of T actually? Tell me. Your M of T minus M of T alternatively changing with the carrier frequency. What exactly is that? It is nothing but M of T is a square wave, yes or no? Yes or no? Come on, tell me. Right. What is that going to give you? M of T multiplied by a square wave, what is going to give you? And after there is a filter, what is going to give you? ds dsc. Hope all of you are understanding this, right? It's a simple concept. I've understood this. Okay. This is called as, this method is called as square law modulator. Because we are using here a square wave. So what is important here in this point is Fourier series representation of square wave. Because of that, you will be able to understand this concept. Fine? Okay. I will change it. Don't worry. Okay. I'll change it. Okay. So